The fourth lesson in our atomic structure and nuclear decay unit is on chemical bonding and its different types. Taking a look at our learning targets and standards here. In this video we are working on predicting the type of bond that would occur between two elements. So let's think about ion formation and what we have learned so far about the octet rule and how atoms form ions. We know that when cations form, atoms lose electrons. But where do these lost electrons go? And likewise, when anions form, we know that they gain electrons. Where do these gained electrons come from? Do they just come from nowhere? Well, the answer here is that electrons are transferred from one atom to another. In other words, if a cation formed, that lost electron is being gained by another atom. Or if an atom is forming an anion and gaining an electron, that electron is lost from another atom. So every electron that is gained by one atom is lost by another. So let's consider this whenever we talk about the formation of ions from lithium and fluorine. So lithium we know has one valence electron because it's in group 1. Now we can draw a simple diagram or a simple model to illustrate this. Notice the symbol we have here, Li, is our symbol for lithium. And then all we're concerned about here are the valence electrons. So I just put one dot there next to lithium to represent its one valence electron, where the symbol itself represents the nucleus and all of the inner level electrons that atom would have. Likewise, fluorine has 7 valence electrons because it's in group 17. So here's a simple dot diagram for fluorine, and notice it's 7 valence electrons. And again, the symbol would represent the nucleus and any inner level electrons. Now ask yourself, when lithium forms an ion, is it going to gain or lose electrons, and how many? Well, because it just has one valence electron, it's going to tend to lose that one valence electron. And for fluorine, when it forms an ion, it's going to tend to gain electrons to get to its octet, and it needs to gain one. So what's going to happen here is that lithium will give up its valence electron, and it will be gained by fluorine. And we can show that simply by drawing an arrow going from lithium's valence electron over towards fluorine, as you see there. So what this will result in is ion formation. Because lithium lost an electron, it will now have a 1+ charge. And because the fluorine atom gained an electron, it will now have a 1- charge. So we get a lithium ion, and we get a fluoride ion. So lithium will lose its valence electron to fluorine, and this will result in the ion formation. And notice we now have oppositely charged ions, a positively charged ion, a negatively charged ion. And as many of you might already know, these oppositely charged ions, they're going to be attracted to each other because opposite charges attract. That's a chemical bond. We have now bonded these two atoms, or in this case ions, together. This is an example of an ionic bond. An ionic bond is simply the electrostatic attraction of oppositely charged ions. So electrostatic just means electric charges that do not change. That's what the whole static term comes in there. And because they're oppositely charged, they will be attracted to each other. Let's look at another example. Here we're asked to draw a dot diagram to show how the compound sodium oxide forms. So this would be between the elements sodium and oxygen. So sodium, like lithium, has one valence electron. Oxygen, because it's in group 16, would have 6 valence electrons. So notice I have 6 dots there. Now sodium will want to lose its one valence electron. And so sodium will give up that valence electron to oxygen. So notice now this sodium atom now has a complete octet because it's lost all of its valence electrons. The first inner level that it has would be full, and so it has a complete octet. It's the most stable it can be. But oxygen, though, oxygen now just has 7 valence electrons because it started with 6, it gained 1, it still needs 1 more. So where is it going to come from? Well, it's going to come from a second sodium atom. There's nothing that says that we can't have a second sodium atom here. So if I put a second sodium atom, again, it's going to want to lose its valence electron. Well, oxygen needs 1 more, so sodium will give up its valence electron to go to oxygen. And now notice all the atoms there have a complete octet. Both the sodium atoms have lost their valence electron, The oxygen has gained 2 in order to get to its octet like we would predict, and everything now has an octet. So we form ions here just as we had before. So notice we have 2 separate sodium ions because I have 2 separate sodium atoms. Each of them lost 1 valence electron, so both of them have a 1+ charge. Now oxygen, I just get a single oxide ion because there's only 1 oxygen atom, and it gained 2 electrons, so its charge is 2-. And again, because they're oppositely charged, these ions will be attracted to each other, where the sodium ions will be attracted to the oxide ion and vice versa. So what we want to look at here is ionic bonding occurs whenever 2 elements bond where one element wants to lose electrons and the other wants to gain electrons. Now if we think about that in terms of the types of elements on the periodic table, what we could say is that ionic bonding occurs whenever metals bond with a nonmetal because metals want to lose electrons and nonmetals want to gain electrons. So when you look at your periodic table, if you have an element from the left side, and recall when we say the left side, it's left of that stair-step line that we see on the table. From elements from the left side of the table want to bond with elements from the right side, we will get ionic bonding because we'll have a transfer of electrons. Alright, let's look at a different scenario here. What if 2 fluorine atoms were going to bond together? So fluorine, it's in group 17, so it's going to have 7 valence electrons. So here's 1 fluorine atom with 7 valence electrons. And here's a second, also with 7 valence electrons. According to the octet rule, we know that both of these fluorine atoms need 1 more electron in order to get to their octet. So ask yourself, is there any way for both of the atoms to gain an electron from each other and fill their octets? In other words, could this fluorine atom here on the left gain an electron from the fluorine on the right, and vice versa, in order for them to get to their octets? And the answer to that is no, as far as a traditional gaining of electrons, but there actually is kind of a way. So each of them needs 1 more electron to fill its octet. What if they shared a pair of electrons? So we're not actually giving up an electron. 1 fluorine atom isn't going to completely give its electron to the other and vice versa, but they could share a pair of electrons. So if I just draw those diagrams again, and I do have them closer together here for a reason, what if the fluorine shared a pair, and it just so happens that when we draw this, we have 1 unpaired electron on each dot diagram. What if they shared a pair? And we would represent that by simply drawing a line between the atoms. In a way, you could think about it as connecting the dots there on those unpaired electrons. So if they share a pair, where these 2 electrons here in the middle get to count for both atoms. So if I count the electrons on the fluorine on the left, I have 2, 4, 6, and then these 2 get to count for the fluorine on the left, so that's 8. And on the one on the right, I have 2, 4, 6, and again, these electrons that are being shared also get to count for the one on the right, so that is 8 as well. Okay, so each fluorine atom now has 8 electrons in its outermost energy level. They have reached their octet. They're both as stable as they can possibly be. This is what we call a covalent bond. Now, the word covalent really kind of tells you exactly what's going on here. The valent part referring to valence electrons, of course, and the prefix co, like we see with other words, the prefix co meaning to share. And so we are sharing valence electrons. Now what a covalent bond is, as far as what's actually attracting the atoms together, it's the mutual attraction of 2 nuclei for a shared pair or pairs of electrons. So remember, both of these atoms have positively charged nuclei because they both have protons in their nucleus. Okay, and those 2 nuclei are both attracted to this same shared pair of electrons, because we know electrons are negatively charged. So the atoms are attracted to the same pair of electrons, which keeps the atoms together. So this will occur whenever we have 2 atoms that both want to gain electrons. And so in other words, covalent bonding will occur whenever 2 nonmetals bond. Now let's look at a scenario where in a way, we kind of bond without electrons. Although there are electrons involved, in a way the atoms don't really use electrons. So let's consider 2 lithium atoms. What if they tried to bond? So again, drawing dot diagrams here, lithium has one valence electron. So here are two lithium atoms. Ask yourself, is there any way for both of the atoms to lose an electron? Remember, they have to go somewhere. Those electrons have to go somewhere, because lithium is going to want to lose its valence electron, as with any other metal, and it really can't happen unless we have a whole bunch of atoms. We need lots and lots and lots of lithium atoms. So just putting a bunch of lithium atoms here, and notice they are arranged in a specific pattern. There's a reason for that. We'll talk about that here just a bit. There is this repeating arrangement of atoms that you see there. So we know metals want to lose electrons whenever they bond in order to form their octet. So what will happen with metals whenever they bond together is they form this repeating pattern of atoms. Sometimes the patterns are very simple, sometimes they're very complex. That's really not of our concern at this point. But the point is they will all lose their valence electrons. Now the question is, where do they go? Well, they don't go to any one particular atom. They belong collectively to the entire group. And so what we get is something like this picture that you see over here, and of course I will explain. So here on the left, this is kind of what we have here to start with my dot diagram, where we have the blue plus signs are representative of the nuclei of the atoms, and the red dots you see there are the valence electrons of lithium, or it could be any other metal for that matter. And so what happens is every one of these atoms loses their electrons, but these electrons, they don't just fly out of this structure. What they do is they move from one atom to another, to another, to another, and we say that they are delocalized. So notice this term here, delocalized electrons. In America, we would spell delocalized with a Z. This image comes from somewhere in the UK, which is why you see the S there. But remember, all these nuclei, they're all positively charged, and we essentially have a whole bunch of cations now, because every one of these atoms has lost its valence electrons. So every one of these atoms is positively charged. Well, what holds them together then? Because the atoms themselves are going to repel each other, because all the atoms, they're all cations now, they're all positively charged, they're all going to push against each other. What holds them together is they're all attracted to this same negatively charged C, or swarm, as you can see here, swarm of delocalized electrons. So metallic bonding, if you would like a definition for it, it is when metal cations, and recall cations are positively charged ions, when metal cations are attracted to a delocalized electron cloud. So these electrons that were lost are just freely moving throughout this structure for the metal atoms. And the reason why we have this repeating pattern is it's the only way the metal atoms can, in a way, share all these electrons with each other. There is a name for this. We call these repeating patterns of atoms, we call them crystals. So in other words, metals form crystals whenever they bond. And these positively charged cations are attracted to this negatively charged electron cloud. Alright, last slide here, and I obviously forgot to animate it here, so that's why everything popped up here at once. We'll determine if the bond between the two listed atoms would be ionic, covalent, or metallic. So this first one here, we're given fluorine and nitrogen. What we just want to ask ourselves, with those two atoms, would they want to gain electrons, lose electrons? Is one of them going to gain, one of them going to lose? Do they both want to gain? Do they both want to lose? And remember, that's based on whether or not it's a metal or a nonmetal. Well, both fluorine and nitrogen are nonmetals, so they both want to gain electrons. So what that means is they're going to share the valence electron, so that would be a covalent bond. Same story with nitrogen and nitrogen. Okay, the fact that they're the same element really makes no difference. We still ask ourselves the same question. Nitrogen is a nonmetal, so when nitrogen bonds with nitrogen, they would also share the valence electrons because they both want to gain, and so that would make it a covalent bond. For the next one, we have calcium and chlorine. Well, calcium is a metal, so it wants to lose electrons. Chlorine is a nonmetal, it wants to gain electrons, and so that will be ionic, where calcium will give up a valence electron or more to a chlorine atom, and that would give us an ionic bond. And then finally we have iron and copper. Now obviously both iron and copper are metals, and so this would be a metallic bond. Alright, so in this video we have looked at the different types of bonds. We've given some examples of all the types of bonds. We've given the definition. And we've also been able to predict the type of bond that would occur between two elements.